Hello and welcome. Why are baseball stadiums so cool? Because they have a fan in every seat. That has nothing to do with what we're going to talk about today, but I thought it was funny. So in this video we're going to look at section 8.1, which is about arc lengths. Let's look at the notes. In figure 1 we're looking at some function, just any old function, and the interval from a to b of that function. So it's highlighted in blue, just the interval, that function from the interval from a to b. And the question we're going to ask is, what is the length of that function from x equals a to x equals b? So if you were to walk from the point of that function at x equals a and walk along this curve all the way to the point that's at x equals b, the question is, how far would you have to walk? Well, if this were a line, we would be able to figure it out. We could use the distance formula to find the straight distance from one point to the other along a line. But when it's curved like this, gets a little, it's more of a question. It's a little bit trickier. But thankfully, we have all of our calculus experience and background to bring to the table. So when we see that interval from a to b, immediately we want to chop it up into subintervals, right? Approximate the length of the arc on each subinterval. And the way we can approximate is by using lines, because like we said, we know how to find the distance between two lines. And then we'll just take the limit as the number of subintervals goes to infinity, so that each subinterval gets smaller and smaller and smaller. And our approximations will get better, get closer and closer to the true arc length of the curve. Same basic tools that we used to find the areas under curves. So figure 1 just shows what our goal is. We want to find the arc length from x equals a to x equals b of our function f of x. Figure 2 chops up our subinterval from our interval from a to b into two subintervals, one from a to like the middle, and then from the middle to b is the next subinterval. And we're using a line to approximate, or a segment to be more exact. So we'll use the segment from the point on the function at a to the point on the function at that middle x value, and then the point on the function at that middle x value to the point on the function at b. If we calculate those two distances and add them up, that'll be an approximation for the arc length. Not a very good approximation though. But the more subintervals you use, the smaller these little segments are going to be, and the closer they'll fit or map to the function, the curve of the actual function that we're looking at. In the limit, we're going to get the true arc length of that function. So figure 4 just shows figure 3 just shows more subintervals. Figure 4 is where we're going to take just one little subinterval. So we're going to take one subinterval and try to bring this picture into math symbols. So suppose on that subinterval, the length of that subinterval is, there we go. Length of that subinterval is delta x, like it always is, right? And then we're going to call the difference from the start y value to the end y value of that line, we're going to call that delta y. And we're going to call delta s that arc length of that approximating line or segment. So I just realized maybe S stands for segment. I actually don't know what the S is supposed to stand for, but S for segment sounds pretty good. I hereby declare S stands for segment. Oh boy, people are going to watch this and cringe. So there we just made this little triangle, and we have our approximating arc length delta S as the hypotenuse of our little right triangle. So using the Pythagorean theorem, you can compute delta S as the square root of delta x squared plus delta y squared. Or you can think that this is like a distance formula. Now what we're going to do is then factor out, it seems like there's nothing really to do here, but you can factor out a delta x squared from both of these terms, from the delta x squared and from the delta y squared. And what you'll get is that delta s equals the square root of delta x squared, the one that we factored out, and then open the parenthesis. Then you have a 1 left over from the first term, and a delta y over delta x quantity squared for the second term. So the delta y squared over the delta x squared, you can bring those under a common exponent. So you have delta y over delta x squared. Now here's where we're going to bring something in from Calculus 1 that in Calculus 1 you didn't really use quite as much, which is the mean value theorem. You use it, but not quite as much as other situations. So by the mean value theorem, there must be some x sub I star, so some x value inside the subinterval, and here's the subinterval we're talking about is from x0 to x1, or from a to whatever this right endpoint of the subinterval is, such that the slope of the secant line, the delta y over delta x, the slope of that secant line going from one point to the other on the function, is equal to the slope of the tangent line at x sub I star. So in our picture, that would look something like, let me draw a different. That would be maybe a point like right here. If you take the slope of the tangent line at that x value, the slope of the tangent line there matches the slope of the secant line that our approximating arc length is going through. So this happens at some delta x, sorry, some x sub I star. X sub I star, that's where x sub I star would be. So what that means is, by the mean value theorem, we can replace the delta y over delta x with f prime of x sub I star for some x sub I star inside of our subinterval. That replacement allows us to go from the slope of a secant line into the slope of a tangent line. We can be talking about the derivative of the function, which is useful here because we'll be able to take the derivatives of our functions. So you have delta s equals the square root of 1 plus f prime of x sub I star quantity squared, and then times delta x. Now the approximate arc length then is going to be the sum of all those little arc lengths that we add up together. Do that for every subinterval. So it's the sum as I goes from 1 to n of the square root of 1 plus f prime of x sub I star. So x sub I star again is just a little x value inside each subinterval, where the derivative at that x value is going to be the same as the slope of the secant line, the slope of the little approximating line segment. So f prime of x sub I star squared, and then times delta x. Now we can take that Riemann sum, so this is in the form of a Riemann sum, take the limit as n approaches infinity. So in other words, the number of subintervals are going to infinity, each one is shrinking in size, the delta x's are getting smaller. And we get the integral from a to b of ds, which ds here is representing delta s, but in the limit. So this is like an infinitely small piece of that graph of the function, that arc. So that's going to be equal to the integral from a to b of the square root of 1 plus f prime of x squared dx. So this integral is the integral that finds the arc length. The more formal statement, if we want to put that together, is if f prime is continuous on the interval from a to b, where there's a little note down there that mentions what that means. That says that the curve has to be smooth, meaning it can't have any breaks, like a discontinuity or any kind of corners. So any kind of corners where maybe it's continuous, but the derivative doesn't exist, or any cusps as well, which are like the infinitely sharp corners. So as long as that's true, then the length, or the arc length, as it's called, of the curve y equals f of x from a comma f of a to b comma f of b, so from the start of the curve to the end of the curve, is given by, here we're just using L to represent that, the integral from a to b of the square root of 1 plus f prime of x squared dx. Using Leibniz notation, instead of f prime of x, you could use dy dx. And that's a little more reminiscent of the delta y over delta x that we had before. If you look at this version, the integral from a to b of the square root of 1 plus dy dx squared and then dx, that looks like the delta x squared that we factored out and brought out of the square root, but just with all the deltas turned into d's. So when you look at that, you can imagine that process that we used to derive the arc length formula. So thank you for watching this video. In the next video, we're going to actually do an example. Thanks for watching, and see you in the next part.